Let's see if we can actually get out early for once. I always keep trying to say this. Calc 2, Lecture 7. So in today's lecture, the major thing in today's is integration by parts. And that'll be taking us through the first half of this lecture, and the second half of the lecture will take us through some parametrics and parametric derivatives. Just, should be relatively review for most of you in regards to parametrics, since you've probably been kind of covering it in some physics aspects. So integration by parts. So integration by parts is a reverse product rule. Reverse chain rule would be the U substitution, right? So with integration by parts, the idea here is that we're going to define y. We have, in a product rule, we have y which is equal to u of x times v of x. So both u and v are functions of x. And then we want to take the derivative of u times v, right? And when we take the derivative of u times v, I get v times du dx plus u times dv dx. U prime v times plus v prime u, but just written in a little different order, so that helps us recognize what the product rule looks like. And then we're going to integrate. So that's the product rule, right? Right. That what we see right there, that's our normal product rule. If we see a function times a function, it's not just a derivative of the two. We can now integrate both of these with respect to x. And the tricky thing here is that these are not canceling out, but the premise is that we've taken the derivative with respect to x, so now we have a function of x, and then we're going to integrate with respect to x. So they are like inverse properties, or they are taking derivative and integrating, but we kind of like to think as a shortcut way in our mind that they cancel each other out, but it's not. It's just saying that with respect to each variable is the same, which undoes it. This gives us that u times v would be equal to the integral of v times du plus the integral of u times dv. It's a function. It's dv being again, it's u is a function of x and so forth, and v is a function of x. So just like what I showed you when we're taking a derivative, if u is a function of x, then u prime, or then du would equal that function times dx. And we are going to just solve for the first piece right in here, or we're going to solve for the second piece. So we'll subtract the integral of v du from both sides, v times du. And then what we get is that the integral of u dv is equal to u times v minus the integral of v du. And this is the integration by parts formula. Okay. Now, it should also be noted, just to please, because I know the question is going to come up. If I take the integral from a to b of u dv, it's going to be equal to u times v evaluated from a to b minus the integral from a to b of v du. So let's look at a couple of examples of the product rule in action. So basically, one of the most common ways to identify integration by parts is you look at something and you say, you know what, I can take the derivative of that, but I don't know how to take the integral of it. Or there might be a function that I can take a derivative and a function I can take an integral, but they don't work together. U substitution and chain rule just doesn't work. So the most common example of integration by parts is integrating the natural log of x dx. The natural log of x is a function that we know how to take the derivative of, and we have it memorized. That's one of those things you should know cold, right? But integral, now some of you that have done this might have memorized the integral, but it's not a common, or it's not an integral that we should be knowing just right off the top of our head. And as such, we're going to identify this natural log as my u, and then this dx, the other, whatever is left over, it could be another function as well, as we'll see, as my dv. So u equals ln of x, dv equals dx. And what we're going to do with u is we're going to take the derivative, so like how we normally do, or with the substitution. So du is going to equal to 1 over x dx. And we're going to integrate the other side, which was going to give me that v is just equal to x, because of course there is an imaginary 1 right here. So the function is 1 dx for dv. Okay? And now we're just going to utilize this method, this formula right here, and that gives us that this integral is equal to u times v, all right? And sometimes, I'm going to write it in the format that's right here. Natural log of x times x. Oftentimes we like to write the x in front of the natural log of x. It just looks cleaner, and I'm going to write my final answer that way. And the same thing will go on the other side. If you can do some mental math, or math in your head, and if I multiply these, that's going to give me a negative, or it's going to give me 2 over x squared, or if you can do that, it'll save you a little bit of time, and it'll clean it up. You can get lost in that work. So sorry, minus the integral, not an equals, of v, which is x, times 1 over x dx. Now, this is one of those problems that once you've done that, now it becomes a function plus there's an integral in there that you can evaluate. That's the nice thing about I consider these like level 1 type of integration by parts. And so we know these x's cancel each other out right there. So we just get 1 dx. So this gives me x, natural log of x, minus the integral of 1, which is x, plus that constant of integration. All right. So again, very common integral problem. I believe I have one on, there's another type of one like that, arctangent, right, or arcsine. We know how to take the derivatives of those. But if I wanted to integrate those, that'd be a good example of another type of problem to practice with in doing it. It would align very much like this one right here. Questions? All right. Now let's go into the more traditional ones that require more than one step, less traditional ones that require more than one step. In this example, we're going to integrate, well, I guess this one has more than one step. We're going to integrate x, x cubed. You know what? I don't need to do that example. It's the same thing. X cubed sine of x. I had another example in there, and I think it's the same idea. It was x e to the negative x, which is just basically the same thing as the first one. So on this type of problem right here, we're looking at this, and we have, typically in these problems you have, you can choose, like, hey, I know how to integrate all of these functions. I know how to integrate, you deal with a polynomial, you deal with a trig, you deal with an exponential. You can you can differentiate all of these. And my recommendation for the most part is you should, in most cases, this should be your first choice for your, for you. So if you have the options, it's typically going to be made easier, or the problem might only be doable by choosing u is the polynomial. And the reason why is, like, sometimes we have to do the integration by parts multiple times and do it more and more and more. And the premise is that if you keep the polynomial as your u, eventually it'll cancel out to 0, okay? And yes, I know some of you are probably thinking, isn't there another way of simplifying that type of way? We'll talk about that in the next example, or the next process of the notes. So in this problem, I'm going to define my u as x cubed, and I'll define the whole thing over here as my dv. And it's not just u as the first thing, the first term, okay? It could have been a situation where sine of x might have been u, and then the other function might have been your dv with the dx. All right, so u equals x cubed, dv equals sine of x. So du is 3x squared, and v is equal to the integral, not the derivative, so negative cosine of x dx. You know, a couple of things that you just might overlook. When you're integrating the dv, you're going to get that dx. Oh, no, I got it backwards, huh? So I didn't see, and that's because I haven't practiced in such a long time. 3x squared dx, and then this is sine of x dx. Will it change your answer? Will we subtract some points from you? Probably not if you don't miss those dx's, but it really makes sure that it really helps you that when you utilize that formula, you know you've done it correctly. It's not common to like take derivative points off from you if you just forgot the little dx, or if you forgot the little plus the constant of integration, or if it's going to be very minimal in terms of it. So just something to know. But you should do. I feel like it makes your work much better. All right, so we have u, v, which is going to give me, again, I'm doing mental math. I'm multiplying them, so I'm going to get negative x cubed cosine of x. I could have written that as x cubed times negative cosine of x, but why not just clean it up right now? Minus the integral, and yes, this is another scenario where you can clean up the math. I would say that the biggest mistake individuals have with integration by parts is typically tracking the negatives in the coefficients. Okay, because distributive property, you might forget a distributive property, you might make an incorrect sign. So VDU, which is going to be
negative cosine x.
Negative. Let's clean it up. Negative. Yeah, 3x squared cosine x dx. And you're right. That's what it is. It makes it a little cleaner for that next little step. And what do we notice? You can take out the negative, or now it's going to turn that into a plus an integral. Okay. Now, you could take out the 3, and that is a valid step. I'm just going to keep that 3x squared inside of there so that you can see the process that I'm about to do, which is called the tabular method. So I'm going to keep the 3x squared inside there. And technically, it would be a minus 3x squared, but you can see that those negatives would cancel each other out. And so once again, I'm going to do u, and this being my dv. So u equals 3x squared. I prefer this way because if you factor out the 3, what's going to happen? Well, why is that going to become complicated for you? Why is that going to probably make a mistake for you? You got to keep that 3 in front of everything. You're going to have to use the distributive probably with the 3 in front of everything. And then on the next one, there's one more. There's going to be one more row again. If you're going to pull out that from the front of the integral, you have to distribute and then redistribute. So it's just better, just deal with the signs and leave everything in there because you don't want to mess with that distributive property. 3x squared, v equals cosine of x dx. So du is equal to 6x dx, and dv is positive sine of x dx. The negative should be the only thing that you're trying to track to, because if this was still a negative, what would have happened is that, of course, you're going to have to track the distributive of the negative, but that's the biggest thing that you want to try to track is the negative, not also the coefficients. I did. Equals 3x squared. Du is 6x dx. And I'm just, I get what you're saying. But yeah. That comes from me just being rusty in terms of it. I still did it?
You have V equals sin x dx.
Oh, I keep writing the dx. Okay, so that was my tracking. Ta-da! Good tracking. That happens to you, I won't take points. All right, so negative, something that some people want to write, if you want to just, use your quotation marks here, or, this is another way of saying it's the same thing from what was already there. That's all fine. I like to actually just write everything else still out. So negative x cubed cosine of x plus, and I'm going to use that bracket here because if that was still a minus, I want you to make sure that it's minus times the quantity of everything inside, okay? Right here, of course, plus. Then the plus doesn't do anything. But if you stay in the habit of doing it, when it's a minus, you'll remember to distribute that minus in your next step. I also suggest take a little bit of time to rewrite it with distributing that negative if it was there before you go on to your next integral or your next integration by part step. So that gives me uv, which is 3x squared. And I don't know why I have the notes right here, but I like to actually just do the problem. 3x squared sine of x minus the integral of 6x sine of x dx. And yeah, again, in this case, the brackets don't do anything, so I don't need to clean that up. All right, well, one more time. U dv. U is 6x. dv is sine of x dx. So du is 6 dx. And v is negative cosine of x. There we go. All right. So this equals negative x cubed cosine of x plus 3x squared sine of x minus bracket, okay, uv, which is negative 6x cosine of x minus the integral of v du, which is negative 6 cosine of x dx. You can see what I mean by there's a lot of sometimes negatives that you have to track. So, and if you can do the mental math, you say, oh, that's negative, so that's going to already give me a positive after you've done a lot of practice. If you haven't done this in a while or if you've never done it, especially, I would have probably put a plus right at the beginning because I knew the last thing was going to be negative inside the integrand. So I would have already hit that plus. And then I need to distribute this out. So it's actually going to be a plus and a minus, right? So it's going to be actually a plus and a minus integral that's going to happen right here. So I could integrate that last little piece. So negative x cubed cosine of x plus 3x squared sine of x plus 6x cosine of x minus the integral of 6 cosine of x, which I can do, which is still minus, right? 6 sine of x plus c. Yes.
Will the original formula, will that be on our equation sheet, or do we have to memorize that?
You have to memorize that.
Okay.
Good question. Okay. So that seemed quite ugly, right? That seemed unnecessary. For those of you who have probably learned this, there is a more efficient way of doing this problem that will take it'll take half the space and less than half the work to do. And that, let me see, make sure. I see a lot of good writing. I don't want to interrupt if you're going. So that is called the tabular method. Now, there are multiple ways of setting up the tabular method. The way I'm going to show you the tabular method is the version that I learned in how I like to organize mine. If you have already learned the tabular method and keeping everything on the same row, that's what's going to be different than mine. I like to angle down. If you've done the tabular method and you've done everything in the same row, keep doing it, okay? It is not, you don't have to set up. Tabular method is just a method of setting it up so that you find, and you have to, because it's showing your work the same thing. I find it interesting because how I've learned it is slightly different, and just kind of the way it feels in my mind that I always track. And again, there's two different ways. Who's seen Stand and Deliver? Again, another calculus / MIT movie that you need to watch before you start the school year. So maybe movie night, people. Stand and Deliver, 21, some good movie night movies for you guys if you're just hanging out and about, all right? You got my recommendations on those. Stand and Deliver is like the all-time classic, my favorite movie of all time growing up. Well, once I was in high school and stuff like that. Yes.
Can you put the recommendations on?
On Slack, maybe, on the Slack group. There, maybe I could do that. But it's a movie about calculus. And I heard some of you are from at least L.A.
San Diego.
Yes, so the L.A. area. Who is from L.A.?
Aren't you from
Oh, you're not from LA? Well, yes, I'm from
Yes, you were from L.A.
Well, I mean, we're both from LA.
The movie takes place at a high school in East L.A.
We're both from LA.
Okay. She's like, who's from LA? All right. So this method only works. It only works if u is equal to a polynomial and you are able to continuously integrate the dv. And in most cases of these problems, your dv is going to either equal to a trig function like sine or cosine, or dv is equal to an exponential function. Those are pretty much the times you would use this method. So you have some polynomial.
They're so similar, bro. Oh, God.
Yeah. Got to get used to your own writing, right? So here it goes. Here's the example. The integral of x cubed sine of x dx. And so this is a case exactly where our u is a polynomial and we can continuously integrate sine of x. So u is x cubed and dv is sine of x dx. Now that's not typically how we write it, so here's how the tabular method and again, there's other versions, and I have a feeling, because we just, Gwen just covered this with our IPX students as well in the workshop, and I have a feeling you did it differently than probably I would do it, which is perfectly fine. I'm not going to teach them in IPX. If you want to show them your way, which like I said, I'm pretty sure that yours is going to be different than mine.
Okay, let's see.
Let's see. My u is x cubed. This is what I'm going to be taking the derivative of. And my integral, my dv, is sine of x. Okay. And I'm going to add some rows. Plus, minus, plus, minus. Now, how do you know how many to go? Just keep taking your derivative until it goes to 0.
Basically the same.
I say it does the same thing. It's just how you align and where you start your plus minuses. 6x, 6, and 0. So I know I've reached the right one. That's where I'm going to stop. And technically, yeah, you don't need that last signage, or you don't technically need it. Also, what's different in the way I do it, and this is also probably the big kicker that's different than many of the methods, is I think of it as the middle term, not as a multiplication term, okay? So some people will show you tabular method when they're saying that plus means all of the signs are plus for that one, whereas the minus says you're multiplying the minus in front of it. I like to think of it as how I would read it, right? This and this and this minus all of these terms. There's two different ways that you hear it, and it's just the way that you're taught, okay? Which one do you do?
Me?
Yeah.
Well, honestly, I learned tabular method yesterday for the
Oh.
IPX, and I loved it.
Did you use my notes from the previous year?
No, I just
It was
looked
there
at-
right there.
I looked at a image on Google, and I was like, whoa, that's crazy.
All right. So integral of sine of x is negative cosine of x. Integral of negative cosine x. Integral of negative sine of x. Integral of cosine of x. Positive sine. And the tabular method, the way again I like it, it's just these two times. Oh, let me actually. I'm going to use a highlighter on this one. Here times here. So basically, it's here times here, minus here times here, plus here times here, minus here times here. Watch. Equals. I could have switched the colors. Let me switch my colors to organize it for you to see. Okay. So I'm just gonna change colors for you so you can track it. All right, so equals negative x cubed cosine of x minus negative negative. So I'm going to switch this to a plus because it's minus minus. Does everybody track that? So basically, I didn't even just write it. So it's negative 3x squared sine of x. You know, that's what it is. That's why it just became a plus. Okay? Plus 6x cosine of x minus 6 sine of x plus the constant of integration. Done. And again, I was switching colors, and I did this piece right here because it was minus a minus. So and as practicing, I would have just done a single plus right in here, and I'd be done with it. And if I look above, they're the same things. Same answer as just what you did before, and look at how much space it took here. Like if I zoomed in, that's the whole problem right there. I could have actually probably fit it into the little side versus all of those steps. Repeated integration by parts. So the idea here is that there is an infinite loop of integration by parts. That if you keep doing it, you're going to keep going on forever unless you realize there's another mathematical algebraic way to do it for you. So it's an infinite loop of integration by parts. Let's look at an example. And we'll see where that infinite loop happens. So the example here is we're looking at the integral of e to the 2x cosine of 3x dx. Okay, very common problem. Usually these problems are mostly always one is trig, one is integral. Okay. I personally like to use e to the x as my u. I like to use my exponential as my u. If you flip it and you use u as cosine, as the trig function cosine, and then your dv as the exponential, your answers will look differently, but they are the same. And the reason that they're the same is because you know how you can write like, it comes from this idea of hyperbolic functions from pre-calculus that you can rewrite them as the same, but they're off by a constant. So this is equal to this, but they're off by a constant. And there's the plus e. So although they look different from if you do it u is e to the 2x or versus u is cosine of 3x, although they look different, they are technically the same answer off by a constant. All right. If you want a little bit more of a challenge, you can flip it on this one as a practice and then see if you can get to the same answer or why. I'm trying to show why. I'm not going to test that, but that's something just a little bit extra to know. So here, I'm going to do my u is e to the 2x, and my dv is cosine of 3x dx, which gives me that du is 2e to the 2x dx, and my v would be 1/3, because we're integrating, sine of 3x. Okay, so I do that, and I get that this is equal to uv, which is 1/3 e to the 2x sine of 3x minus the integral of v du, which is going to be 2/3 e to the 2x sine of 3x dx. Okay. We'll now do it again, just like we did. It kind of feels like that first problem a long way. U is, what are we going to set as U? Yeah, 2/3 e to the 2x, and my dv, sine of 3x dx. So du is 4/3 e to the 2x dx, and my v is negative 1/3 cosine of 3x. So now I have 1/3 e to the 2x sine of 3x minus, bracket, I like to use my bracket here, uv, so minus what? Minus 2/9 e to the 2x cosine 3x minus the integral v du, which is again another minus. If you can, I personally like to, I have a minus, so I'm going to change this to a plus right here because it's a minus, so I'm going to get 4/9 e to the 2x cosine 3x dx. And again, if you don't like, I put it as a plus right there because there was a minus that became a plus right there in that term. I'm going to expand this out just to make it a little cleaner. 1/3 e to the 2x sine of 3x plus 2/9 e to the 2x cosine of 3x. And here's where I'm going to start. I'm going to change things up because what we have here, and we should see, is that this integral the integral of the functions mimics the same thing but off by a multiple. I got back basically. So what I'm going to do when I do this right now, I'm going to rewrite this as plus. I'm going to factor it out. I am going to factor it out right now. 4/9 the integral of e to the 2x cosine 3x dx. It works the same if the 4/9 was inside the integral, but I kind of really do want to show you and let you see what's happening, especially in these lecture notes. So this is equal to the integral of e to the 2x cosine 3x. Huh? Oh, it is a minus. Correct. See, distributive property practice. Don't forget, I distributed here, but I got to then redistribute here. And so in this case, it'd be like a minus, and a minus. It's the hardest thing. So it's a minus 4/9 right there. Dx. Well, what I'm going to do on this problem, let's, hey, I can recognize, this is just something, I can see that this and this are the same. What I want to find is in terms of myself. So what I'm going to do is I'm going to rewrite this as, I'm just going to call it I, because it's an integral. I could have called it X, I could call it V, I can call it whatever I want. I is equal to this, and so now I have I equals 1/3 e to the 2x sine of 3x plus 2/9 e to the 2x cosine of 3x minus 4/9 I. And now it's an algebra problem. I want to find I. I is what I'm looking for. So we're going to solve for I. So I'm going to add 4/9 I, what I'm looking for, the integral. I'm going to add 4/9 I over here. That gives me 13/9 I equals 1/3 e to the 2x sine of 3x plus 2/9 e to the 2x cosine 3x. This would have been a great place to put those ditto marks, or, you know, I like to use my squiggly with the 2's. It makes it a lot more easier here. And then I multiply by the reciprocal. So I'm going to multiply this by 9/13. I'm going to multiply this by 9/13. And I get that my integral, my initial integral is equal to, and I could have just put this plus c. I can, right? I can just say that plus c. But I'm going to distribute it out. So I would get, what is that, 3 13ths? Because the 9's cancel each other out. E to the 2x sine of 3x plus 2/13 e to the 2x cosine of 3x plus the constant of integration. So that's the repeated type of one. So those are the three, you know, tabular method type problem where it's repeating over and over and over. You might just have a problem where you might just use a integration by parts and be able to integrate. And then there's this type of problem where basically what you're looking for, if you have a trig and an exponential, it's always going to be this type of problem.
How many times do you have to go? Did we go through it more times?
Twice.
You have to go through it 3 times.
You have to go through it twice because the idea is that, well, e to the x, the derivative or the integral of e to the x is always e to the x or e to the u with a constant. And sine and cosine take 2 iterations to come back to itself again on term with again multiplied by a coefficient. So sine becomes cosine and becomes sine. So that's why you have to do 2 integration by parts. Good question. And yes.
So if u has like trigs or exponents, you use the
When u and dv are trig and exponent,
u and dv.
you're going to have this type of problem right here.
Okay. But if it has a polynomial, then you could just do tabular method.
As long as you're able to continuously integrate that dv. If it's something that's really, really ugly, the tabular method might not work best. It might just be a traditional problem where once you clean it up, it might be a chain rule integration for that next piece. So just because it's a polynomial doesn't mean you should do tabular method. You got to ask yourself, if I integrate this other thing, can I integrate that again? And if the answer is like, that's too ugly or I'm not going to be able to, then the answer is don't It's not. It's more. It's going to be a traditional, something that you can integrate. That's something that you can integrate might require some of our past integration techniques. Reduction formulas. All right. So, yes, the answer is yes. These are proofs that you will be asked to do. All right. And what we have here is all about recursive. Think Newton's method as a recursive method and stuff like that with repeated, that is in part a repeated integration by parts. I will give you the reduction formula. This integral reduces down to this integral. And therefore, you need to show me how to get from here to here. And I'm just going to say, prove that this is this. You need to know, oh, that's the integration by parts method that I'm going to have to do. Okay. These are usually back in the back of the textbook. So here's an example. Prove, and then once you see it, I'm going to write one down in here, and then I'm going to show you what does it mean, because some of you might be like, what is a reduction? Prove that the integral of cosine to the nx dx is equal to 1 over n cosine to the n minus 1 of x times sine of x plus, let me just throw this up, plus n minus 1 over n integral of cosine to the n minus 2 of x dx. So basically what a reduction formula does is it reduces down to something that we should be able to eventually integrate. So for example, if this was cosine cubed and we applied this formula, then we would be able to get the first terms, and it would be minus cosine of x dx, because it went from cube to 1. So we reduced it from something that was cubic to something that is power 1, and now we can integrate it. If I started with like the 8th power, think about those problems. We know the method to do it for the 8th power, but all that work, and it would be really crazy. So it can go from cosine to the 8th to an integral of cosine to the 6th, and then you would reapply the reduction formula again to go from the 6th to the 4th, apply it again, 4 to 2, and then either do it one more time, or you can actually integrate, but you can use it again. And I could ask you then to evaluate it. So please be aware that I could ask you to find and prove the reduction formula and then to use it at the end what your final answer is. So not only prove it, but then actually do it with all those distributives. So you can think of this, basically it's a reduction. So this is going to be my I over here. And then when you look at this problem, you know you're going to have a U and a V that are going to be inside the problem. And so when you're thinking about these types of problems, you know that this piece right in here, this is going to be my U times V. And I'm going to put that in quotation marks because that's like your hint. The terms that are in front, the first terms are going to be your U times V. And that's why you're going to get the U times V. What about this 1 over n? That 1 over n should come from using the I part in solving for I. So you're going to have it in terms of an n, and then you're going to do some algebra like we did over here where we had that 9/13, which in this case is going to become 1 over n. Okay? So we're going to have like ni. And then I would multiply both sides by 1 over n, and I would get that. So that's your kind of hint right here. So if I know that my u and my v, that either one of these two, I don't know which is going to be which, my u is going to be cosine or my u is going to be sine, I got to ask myself, how do I make cosine into one of those? Well, that's easy, right? All right, but this is the same thing as the integral of cosine of to the n minus 1 of x times cosine of x dx. Because when I do that, now I can see, hey, there is my u. And I knew one of these two terms right here was going to be my u. So there's my u, which means my other piece over here is now my dv. So u is cosine n minus 1 x. And there's technically another way of doing this one. There is another way of doing it where your u is cosine to the n minus 2. You could do it that way, and then you're left with sine squared, or cosine squared, which becomes 1 minus sine squared. It works, you get to the same thing. So this is kind of like there's more ways to try to do it. My personal preference is always look to here. I want one of these to be my u. Question?
Just like on how you got from the top to.
Oh, I rewrote here. So this is still cosine of the nx because there's an imaginary 1 power right here. So I'm breaking up my cosine to the nx.
Oh wait, that's not cosine to the n times x.
That's n minus 1.
Thank you.
Do you want me to see? Yeah. What's your question?
Oh, yeah.
So dv is cosine of x dx. All right, so du, and this is where again it gets a little ugly as well. My du is, gotta be careful, what is my du? N minus 1 cosine to the power of
N minus 2
of x
over
times negative sine of x dx. Chain rule. And my v is sine of x. So that's got to be careful about that. And that's why, you had to use chain rule on that part. All right. So now we have that I.
You can power rule a cosine function.
Yeah, because technically, cosine n minus 1 of x is the same thing as cosine of x all raised to the n minus 1. And so I hit here, that stays, keep the baby inside, and don't forget the baby. So,
I would never.
cosine of nx, I'll write the parentheses, the integral of cosine of the nx dx is equal to u times v, right? Which is cosine to the power n minus 1 of x. I know I'm adding a parentheses now because it's getting hard for me to track them as well. Times sine of x minus the integral. Well, wait a minute. There is another minus in here, but I'm just going to write it all the way out. N minus 1 cosine to the power n minus 2 of x times negative sine of x dx. Oh, I'm missing. That's v du, so times sine. Oh no, I'm sine, so sine squared of x dx. Let me do it this way so you can track why it's sine squared. That's sine because it's these two right here gives me the sine squared, and then this just becomes a plus because of that line right there. Good? Okay. I don't want to move.
Oh, this is just integration by.
It's integration by parts. UDV. adding them together, the sine to the sine, it gave me the sine squared. All right, so really I just have to work on that other piece right in there. So that becomes, now the trick to do this type of problem is I'm gonna need to integrate. You shouldn't need the integration by parts again. You should just need to actually integrate this last piece right here, okay? So there's a sine, there's a cosine, and at least one, and then we have the sine squared here. So what is the method that we know to do? We can turn this into what? 1 minus cosine squared. And so that's what I'm about to do on the next line. So this is equal to cosine to the n minus 1 of x times sine of x plus n minus 1. I'm going to pull it out there because I'm not going to do integration by parts, times the integral of cosine to the n minus 2 of x times 1 minus cosine squared of x dx. That's equal, okay? Now, if you notice, now it's looking a lot like what we were trying to prove, right?
Wait, so where did we get sine squared of x from?
Sine times sine. That's why I put them in red.
Oh, because du also has a sine.
So this becomes cosine to the n minus 1 of x times sine of x plus n minus 1 times the integral of, times the integral of, do I need it? No, I don't need it there. I'm going to use the distributive property. We here, in there, so that's going to be cosine n minus 2 x minus what? Cosine n of x dx. And voila, that's what I was looking for right there. So what I was looking for this whole time was to get something that was back into my first original integral. And there it is right there. This little piece is going to hang around. I'm not going to do anything with that because that's in my reduction formula. So now I have that I is equal to the cosine of n minus 1 of x times sine of x plus n minus 1 times the integral of cosine of n minus 2 x dx minus parentheses n minus 1 I. That's for me distributing, taking there, and going over here. So this becomes a minus. I'm just separating this as an integral and an integral, right? So it's integral with distributing right here. That's why I get 1. I get here, right here. And of course, well, isn't that just 1 minus n? True, but don't need to do the work. Just leave it as minus that because we're going to have to add it to both sides and do some algebra right now. Questions tracking what I just did? Mm-hmm. I haven't integrated anything. I just get the same integral. So this becomes the integral of cosine n of x, which is what I had started with. Sorry, which is the whole thing I was started with right there. So this integral, and that's where the I comes from. So now I'm just going to do some algebra. I'm going to add n minus 1 I to both sides. And if I add one I to n minus 1 i's, I get, what was it? N i's. Yeah, so ni equals cosine n minus 1, and x times sine of x plus n minus 1 integral cosine n to the power n minus 2 of x dx. And I'm going to multiply both sides by 1 over n, which gives me that my integral is equal to 1 over n cosine to the n minus 1 of x sine of x plus n minus 1 over n integral cosine to the n minus 2 of x dx, and that is what I was trying to prove, and I've proven the reduction formula. Sorry, I zoomed up too fast. I have fun with these. You can do it from a lot of all the different trig functions. There's a reduction. Typically, again, if you look at the back of the textbooks, these are the ones that you're trying to look at. Secant, you can do secant, you can do sine, you can do tangent, you can do all of those different ones.
How did we go from cosine to the n minus 2x dx?
It's when I changed sine squared into 1 minus cosine squared, and then I distributed. So I changed the sine squared to 1 minus cosine squared, and then I distributed the cosine squared, the cosine n minus 2. Let me zoom out one more, right there. So I changed the sine squared to 1 minus cosine squared. And again, the goal was to get another version of what I started with.
How did you go from negative cosine nx to negative n minus 1? Where's that n minus 1 come from?
Where does this come from?
Yeah.
Distributive property from here,
Oh.
which came from the chain rule of my derivative of u. Good questions? All right. Take it down a little bit now. So let's now talk, and I know you've been probably covering this already. Let's switch it up, basically going into the start of our next part of notes, which we'll continue on in our next lecture as well. But we're gonna talk about rectilinear motion in the beginning of our next lecture. But before we get there, let's talk about just parametric. I know it's like, wait a minute, my whole brain was wrapped around this. That's what I was wanting to see. So let's talk just about parametric equations for the last 8 minutes of lecture. I can do it. I was going to say, well, because that seems too early to just call it now, right? There's a lot of like, whew.
No, it's never too early.
I think that would be a good time.
Yeah.
It's too early.
I think we leave it up to Daniel.
We put
Oh,
some
my
other
Daniel.
accepted.
Why would Daniel and Daniel allow me to know what y'all talking about?
It's only 8 minutes.
7 now.
Almost 6.
I'm locked in, bro.
To make up for the 2 minutes we've been over.
Yeah.
past
Well, I
class.
hate you, man.
All right, let's call it.